When I had the news of the Nobel Prize, I felt, there must be something wrong there. But with the time, I got used to that. And anyway, I don't think I can do anything about it.
There's always something especially magical about listening to Nobel laureates describe how truly surprised some of them are to receive the call from Stockholm. And in this conversation with Pierre Agostini, I got a real sense of his playfulness of spirit, as well as an introduction to some pretty deep physics. There's a lovely moment, for instance, where he describes the panic that set in when he wondered whether he could actually reproduce his groundbreaking result. And then we get to talking about the fact that time is not perhaps infinitely divisible, which is a pretty mind-bending concept. And like many of these conversations, it leaves me wondering whether there is any age limit to scientific creativity, which opens up the whole difficult question of how you distribute the jobs between the young and the older. And that's something we go on to discuss. So I leave you in the hands of Pierre Agostini.
This is Nobel Prize Conversations. Our guest is Pierre Agostini, the 2023 Physics Laureate. He was awarded the prize for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. He shared the prize with Anne-Louis Lié and Ferenc Krauss. Your host is Adam Smith, Chief Scientific Officer at Nobel Prize Outreach. This podcast was produced in cooperation with Fundación Ramón Arefes. Pierre Agostini is Emeritus Professor at The Ohio State University in Columbus, Ohio. He was a researcher at CEA-Saclay in Paris from 1968 to 2002. He speaks to Adam about contradicting Einstein, how forced retirement can sideline scientists at the top of their games, and the strange things that happen as you approach the very smallest units of time. But first, green cards, transatlantic flights, and feeling at home in two places at once.
You live in two cultures. You live in Paris, but also travel to Ohio State University.
Yeah, I just spent a month and a half in Ohio, and I'm just back now.
And how do you find this coexistence of living in two countries at once?
That's a little bit difficult sometimes, especially because I am on the green card program. And on the green card, we are supposed to spend at least 6 months in the States. And I'm not. So each time I go back, I have to explain that to the officer. But otherwise, it's okay. I'm very used to both places. And I feel at home both in Ohio, in Columbus, and in Paris.
It's nice to have two homes. From a scientific culture point of view, do you find that there is a different approach at all to science in Paris and in Columbus, Ohio? I mean, obviously science is universal, but the differences are interesting.
Well, especially in this circumstance of the Nobel Prize. I mean, they had organized this month in Ohio State like something full of ceremonies, and it was really very different from the atmosphere here in Paris. Yeah, the people at Saclay are okay, but they are not doing the same thing as those guys. Anyway.
Maybe the French are more used to having Nobel laureates in optics.
Perhaps, yeah, that's the case. In Ohio, they told me that I am the first one, so they did a lot.
I'd like to talk about your scientific upbringing, how you started. I mean, you were born in North Africa, but you went to a military school in France. When did you discover that you were scientifically minded?
When I moved from Tunisia to the military school in La Flèche, I had to choose the scientific option, and there was not another solution for this move. And so I had to turn to science. Although until the year before in Tunisia, I was rather classical for classical studies. I mean, Latin and French and stuff like that, literature. But then I had to do it. And it was okay. I mean, I like it. But my previous life was somewhere else. And I turned to science because I had to, and it was really a discovery, and I liked it, really. And I liked especially the math program. And when I went to Marseille to start my university classes, I wanted to do math, but I was discouraged. I mean, people said, "Oh no, it's too difficult. You will not make it in math." And so I took physics, and for me, physics, it was just like any other matter, right? And it's only when I started doing research that I discovered the fun of physics.
So it was a very happy circumstance that you were pushed in this direction. It wasn't so much a choice.
In a sense, yes, I agree.
But you never gave up on your interest in the humanities, did you? You read a lot, and it's always been a big part of life.
Yeah, I should do that when I can. I mean, this few months, my schedule was so tight that I didn't have time to read a lot. But okay, I try to.
That's a bit sad that the Nobel Prize stops you reading.
It's not the Nobel Prize. Oh, yes, it is, after all. Yes.
Can you describe what the excitement was of discovering the joy of physics through research when you were first exposed to it?
First of all, there was some excitement because the subject I started working in, multiphoton ionization, or interaction of strong laser field with matter, was nowhere. There was almost nothing on that in the end of the 60s. And my advisor, my PhD advisor, I told him, okay, I'm going to work on multiphoton ionization. He said, oh, don't do that. He was a spectroscopist, and he did not believe in the strong field business. I mean, the intensity was the parameter that doesn't never show in those spectroscopic studies. That was the first thing. Then there was the excitement of discovering things that nobody has seen before.
Why did you choose this field that you were advised not to go into?
That's an interesting question. Actually, there was someone from Saclay, actually my old friend Yves Gontier, who was a theorist at Saclay at the time, who sort of scouted the university in Marseille, where it had graduated 2 years before. And he was trying to find people to work on the program. So I had an offer of a job before finishing my PhD. And I just took the offer.
Pragmatic, yes.
Yeah.
So this work is, of course, all about the interaction, as you say, of light and matter. It is extraordinary to reflect on the fact that you discovered this phenomenon that was completely unknown, above threshold ionization.
ATI, yes.
I might need a bit of help here, Adam. You talk about multiphoton ionization and above threshold ionization, and I just wondered if you could explain what those are.
Well, yes, I'll try. The ionization is referring to the idea of ejecting an electron from an atom and so creating an ion. And in order to do that, you have to give the electron sufficient energy to escape from the atom. Mm-hmm. And there's a certain threshold of energy it needs. So above threshold ionization just refers to the idea that you're chucking an electron out of an atom with more energy than it actually needs to make that journey from being part of the atom to being expelled. Yeah. And then multiphoton ionization is one way that can happen, that an electron can absorb the energy not just of one photon, one particle of light, but several on its journey out of the atom. And so that way it receives more kicks of energy from these photons, and so is ejected with more than the threshold energy that it needed to get out.
And what's the consequence of it having more energy?
It has a different energy spectrum, so that the ejected electron then occupies a different set of energy levels to what it would have if it had received less energy. And that has all sorts of consequences that have opened up possibilities, such as the creation of these very short pulses of laser light.
That's very helpful, thanks. I do feel like I understand it a lot better now.
I think it's a very superficial understanding.
But it'll do me.
If you're listening to me, I'm afraid.
Well, I'm going to test you again now, because you mentioned strong field physics, and I wondered if you could explain what that is as well.
Yeah, that's just the term that physicists use to refer to this field of study of the interactions of laser light and matter. It's a field that studies ultra-fast processes where light is interacting with matter.
And I think this research extends the work that Einstein did on the photoelectric effect. How does it do this?
So Einstein proposed an explanation for the observed photoelectric effect, which is that if you shine light at a sheet of metal in a particular way, you can get electrons ejected from it. Mm-hmm. And he proposed that the energy that was necessary to make that happen was being transferred to the electrons through individual photons, which had quanta of energy. They were giving their packets of energy to the electrons. And it was his explanation of the photoelectric effect, which was actually the thing that the Nobel Prize committee identified when they awarded him the prize in 1921. And that is, the basis of what is going on here. But with multiphoton ionization, it's not just one photon that is transferring the energy to the electron, it is more than one. So it's absolutely an extension of Einstein. I asked Agostini about following in Einstein's footsteps. So let's listen to what he had to say. There's such a tradition here, there's such a legacy. It must have been so thrilling to feel oneself part of that.
Yeah, we were used a little bit in contradicting Einstein with multiphoton ionization, right? Mm. Because then it takes several photons to ionize, not just one. And so the Einstein law has to be modified a little bit. ATI was one step further. And it was interesting because when we had the first result, I remember it was during the summer, and then we wrote the paper, and it was quickly published. But for a long time, really, we were really worried because we could not reproduce that result. So it took really a long time because we changed laser, we changed the electron spectrometer and so on. So, yeah, the experiment was completely different. And it took us some time to realize what we should do to see the ATI again. And it was really the worst time in my life, I would say, because the paper was published and we could not reproduce it. So
it would have been extremely embarrassing to have contradicted Einstein and then been shown to be wrong.
Yeah, absolutely.
Gosh, I can imagine you remember the sense of relief when the second result came.
Yeah, that was, we could sleep at night again.
Presumably, the environment you found working at Saclay was a very productive and supportive one. So I'm interested that eventually you had to leave Saclay. What prompted the move from Saclay?
Oh, you mean in 2002? Mm. Oh, that was just the rule for retirement. Mm. If you were 60 and above and you had enough years for the pension, you had to retire. There was no choice. I mean, the head of the department had to retire this way. The head of my group had to retire that way. So there was no choice. The rule is no longer that now, and people can work until 70 or something. Mm. But back in that time, it was the rule, and could not avoid it.
It seems a terrific waste of talent to let people go so young. And of course, as you say, it's changed. But what do you think about that? I mean, what do you think about the balance between people who have long track records and the new people coming in? How do you get that right?
I'm not so sure what's the best solution, but certainly being sort of retired at 60 or 61, really, for me, was probably the worst thing possible. I suppose there is always ways to hire young people without retiring all the people.
Sure, sure. In your case, you'd only quite recently done the work which is cited by the Nobel Prize Committee in their award, producing attosecond pulse trains and defining them.
When you do this kind of experiments, I mean, there's always a little bit of luck, I think, involved, because you never know what's going to happen.
Were you very surprised that your experiments yielded the pulse train?
No, we're happy. The surprise was first because we didn't see anything at all in the results. And after we normalized, we divided by the total counts. And then the oscillation sort of by miracle appears at the time. Yes, we were happy. We were expecting that. So it was not a surprise. I mean, the surprise was because at the beginning we didn't see it, the oscillation.
Right. And do you remember what you did when you realized that you were seeing the oscillations?
I think we wrote the paper very quickly.
Adam, I know we've talked about attoseconds in previous episodes, but I think I could do with a little bit of a reminder. What is an attosecond?
An attosecond is 10 to the minus 18 seconds. So that's a 0 followed by a decimal point and 17 zeros in a row before you get to a 1. It's a very short space of time.
I'm remembering now. I can remember telling my kids about it because I just thought it sounded so cool. And what was the specific research that Pierre Agostini did around attoseconds and that he was awarded the prize for?
Well, he got the prize for producing the first pulse of light that was in the attosecond time domain. So he produced a pulse of laser light, in fact, a little sequence of pulses, but the little sequence of pulses lasted just, I think, 250 attoseconds. And he also was able to demonstrate that that was the case, which was far from trivial. But this was the beginning of the race to get shorter and shorter trains of pulses of laser light, and now they're down to a few tens of attoseconds in length.
Amazing.
But basically the production of incredibly short pulses of light.
Which at the time, that must have been quite an amazing thing to sort of realise the ability to do that.
Yes, I mean, I think what was opening out was a whole world of processes which last roughly that long. And so suddenly you can isolate them and see them as never before.
Mm. And we're about to dive into some fairly complicated topics that I haven't heard of before. I wondered if you could help explain some of them.
Sounds scary, yes.
This is not a test. The first is a term positronium.
Yeah, positronium is like hydrogen, which is an electron orbiting a proton. But in the case of positronium, the proton is replaced by another positively charged entity, which is the positron, the antimatter particle to the electron. And since these two annihilate each other when they meet, the positronium is very short-lived. Fascinating, but only briefly there.
I see. And we've talked about attoseconds, but what are zepto and yoctoseconds?
Yeah. Well, things tend to go down in threes. So if you go down 1,000-fold from an attosecond, you get to a zeptosecond, which is 10 to the minus 21 seconds. And another 1,000-fold down will take you to the yoctosecond, 10 to the minus 24 seconds. So I believe a zeptosecond is the shortest period of time ever measured so far. And a yoctosecond is approximately the time it takes light to travel across the distance of the atomic nucleus. So we're down to really, 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 really small things and tiny amounts of time.
I can't get my head around it. It's such a short amount of time.
Yeah, I mean, physicists have it all. They get to study the shortest things and also the biggest things like the cosmos. As you said, it's all pretty cool.
Yeah, very. Does the Planck time help us to understand this better? That's another term I'm not so familiar with.
I think that Planck time takes us into dimensions of beyond our understanding. But the Planck time is the shortest time that anybody can talk about. So it's defined as the time it takes light to travel the Planck length, which doesn't help you very much. But the Planck length is one of those fundamental constants defined by Max Planck over 100 years ago, when he was seeking to establish a set of constants that were based not on things that we measure around us as humans, the meter and the second, but rather units based on the fundamental constants of the universe, like the speed of light. And the Planck time equates to 10 to the minus 43 seconds.
Wow.
And physicists tell us that there's no point in talking about anything shorter. But this was something that I was interested to explore with Agostini, whether that's the end of time or whether you can go still lower. So let's listen to that conversation. At the beginning of your Nobel lecture, you ask a question, which I suppose is one that physicists debate often, but is not something that most people think about, which is time infinitely divisible? The attosecond is, as people keep saying, very, very, very short. But can you just go shorter and shorter and shorter? Or is there a limit to how much you can divide time up? Could you talk about that a little? Because it's such an exciting question.
Oh, okay. After 2001 and the attosecond demonstration, there were a few papers, 5 or 6 papers from the Keitel group in Heidelberg, trying to figure out how we could make even shorter pulses than attosecond and zeptosecond, and even later yoctosecond were in the picture. The solution they proposed is to use positronium or stuff like that to the harmonics, to replace the atoms in the harmonic source. And so it's not completely obvious how you could do that practically. But the attosecond is certainly not a limit. And at least up to or down to zepto or yocto, it's certainly not physically impossible. On the other hand, there is a limit. I mean, the limit is the Planck time, and conceptually, you cannot go beyond that limit. And that limit is 10 minus 44. So we are still very far from it.
I know that the Planck time is the time that light takes to travel the Planck distance, and you can define the speed of light by that. But please, why is that the limit?
Okay, the Planck time is a limit as far as I understand it, because if you look at the spectrum corresponding to this short time, the spectrum, that is the energy, right? The spectrum and the frequency and the energy is the same. This energy is the energy of all the universe. So there is no way you can go beyond that. And then the time is 10 minus 44 seconds.
I guess most people don't think of time and energy being related, but this shows very clearly that they are.
Yes, they are, from the Fourier transform relation.
It's just mind-expanding to think of it, even though it becomes too complicated to think about very quickly. Let me change direction a little bit, please, onto something non-scientific, just how it has been since the announcement of the Nobel Prize, because I am sure that it increased the amount of demands on your time, and you must be receiving invitations to be all over the world all the time. How do you cope with the increased attention?
First, let me tell you something. When I had the first announcement, I felt there must be something wrong there. I didn't feel at all like being in the list of the Nobel Prize, like people like contradicting or Serge Roche or even Alain Aspect and so on. I felt there must be something wrong somewhere. But with the time, I got used to that, and I was always trying to figure out that, okay, there must be other cases where the people didn't feel like they deserved really the Nobel Prize. But okay, so after that, especially after my trip to Ohio State and all the ceremonies and the things that we had there, and meeting the president of the university and so on, I felt a little bit more confident. And anyway, I don't think I can do anything about it.
That's true. It reminds me of a comment made by a laureate I was traveling with last summer. An audience member asked him, does receiving the Nobel Prize make imposter syndrome better or worse? And he answered yes and no. I guess most new Nobel laureates wonder how they fit into the general picture of the list of people who've received it. But at the same time, as you say, it also maybe has the effect of building confidence.
Yeah, for some people, it's almost natural. If I think of contradicting or of Serge Roche, I mean, all the life has been working in one direction. And compared to them, what I did was not comparable at all. But of course, if you think that the Nobel Prize was not just for attosecond, but for things that go back to the 70s, okay, all right, then I have some reason to believe that it was a reasonable choice.
It's the development of an idea. It's the realization of a potential, isn't it?
It's an accumulation of experiments in the strong field physics.
I understand coming to terms with this, it was one aspect of it, but then just the purely practical point of how many people want you and want your time. How do you handle that?
I'm trying to fight for my time. I have the help of Jesse Middleton in Ohio, and we are trying to keep things in a reasonable limit. For instance, I'm declining not most, but at least a lot of those invitations and keeping just a few of them. That's one way of doing it. I'm not sure there's another way.
No. How does the family feel about your prize?
Oh, they were very happy. I mean, first of all, it's my daughter who gave me the news of the Nobel Prize, and she had heard it on internet or something. Yeah, they were happy, and everybody was happy to see my granddaughter, my grandchildren at Stockholm, and especially my grandson.
How old was he when he went to Stockholm?
He's 22 this year, and she's 24.
It's really fascinating to hear your reflections on it, because like it or not, it is a life-changing event, I suppose.
Yes, it is. For the moment, it has been a life-changing event, and it will be like that until at least the end of this year. After that, I hope it's going to be at least slowly returning to normal.
Yes.
It's difficult to work, really. We still have problems with referees and with writing papers in Ohio, and I need time.
So it doesn't make any difference to that side of life at all? No. Maybe it makes life even harder with referees now. I don't know.
Yeah.
It's been so very nice to talk with you. I've enjoyed it very much.
My pleasure.
Thank you.
Thank you.
You just heard Nobel Prize Conversations. If you'd like to learn more about Pierre Agostini, you can go to nobelprize.org, where you'll find a wealth of information about the prizes and the people behind the discoveries. Nobel Prize Conversations is a podcast series with Adam Smith, a co-production of Filt and Nobel Prize Outreach. The producer for this episode was Karin Svensson. The editorial team also includes Andrew Hart, Olivia Lundquist, and me, Claire Brilliant. Music by Epidemic Sound. If you're interested in another conversation about the extraordinary things that happen as you approach singularity, check out our episode with 2020 physics laureate Roger Penrose. You can find previous seasons and conversations on Acast, or wherever you listen to podcasts. Thanks for listening.